Good afternoon, everyone. Or if you're in my time zone and my past self, it is currently 11 p.m. So, how are you guys doing? My name is Howard Montezoka,
I'm Arturo.
and we are going to do blockchain technology. So, who are we? What's presented? I am Howard Montezoka, senior computer science major, fifth year. I am interested in mobile application development.
I'm Arturo Blandon. I'm also a senior computer science major. I'm also in my fifth year. I'm interested in pursuing web development.
We will both be presenting blockchain technology in this order. So we will begin with the what it is and its history, its core architecture, such as blockchain and proof of work, its applications, and a Q&A session. So this is just a general outline of how our presentation is going to look. And now I'm going to hand it off to Arturo.
Right, so a blockchain, what is it? A blockchain is a distributed ledger that is linked cryptographically. In other words, it's a chain of distributed blocks of data that's really hard to modify. So basically, each block contains some data and it's identified by a hash and it links to other blocks through these hashes. It's made with the intention of appealing to a general consensus rather than a single entity. So instead of having a single central server that handles everything or has all the data in it and it's all controlled by a single node, it's more of a peer-to-peer system where all the nodes work together. And in order to determine correctness or what should occur, they use a consensus. So what is the majority or like a 51% type thing. Um, and then, yeah, right there is what I just said. A block will contain a hash of its previous block. So it'll have reference to the previous and it'll have its own hash, a timestamp of the block, and then the data within that block, which will depend on the implementation of the blockchain. The most popular one being which holds actions example. So for the history of blockchains, it has a bit of a rocky history by initially starting as an appearance from a dissertation in 1982 known as Computer Systems, established, maintained, trusted by mutually suspicious groups by cryptographer David Chaum. Um, so it started off as just sort of an idea in this paper where they went over sort of in theory, theoretical, how it would work, etc. And then it's not really talked about much. We don't really hear too much from it. Um, just not too popular yet. And then it appears 9 years later again in 1991 when Stuart Haber and Scott Stornetta wanted to preserve timestamps for documents with the full intention of preventing any sort of tampering. So they wanted to preserve the state and like not allow for any tampering in their documents and yeah, just avoid outside like intervention into their data. Uh, and then once again, there's another long hiatus where not really talked about too much, and it's mostly just people thinking about what could be done with it until in 2008 when a man or a group that we don't know of, known as Satoshi Nakamoto, created its full implementation and he fully implemented blockchain technology and the specific uh, thing that he used it for, as I think most people know, is Bitcoin. Okay, so the core architecture of a blockchain. So how does it look? The blockchain itself is constructed from a Merkle tree. So every leaf node is labeled with a hash, and every non-leaf node has a hash of its children. So it's also known as a binary hash tree. So the way that it works is that um, just going to make it clear that blockchain doesn't necessarily have to do with cryptocurrency or Bitcoin, but I'm going to use Bitcoin as an example here. So a block in the chain doesn't necessarily have a single transaction. It can have multiple transactions, like let's say, for example, 50 transactions in this one block. Um, it doesn't just go through the hash in one go, like that one block is just hash and it makes the hash. It actually goes through every single transaction, or it goes through the tree and it hashes the children and goes upward, like bottom up in the tree, until it comes up with the final hash. So it hashes, then concatenates the hashes, and then hashes that, and then it repeats until all the data in it uh, sort of combines into a single hash, which is the final hash. So that's how that is implemented. It is iterative in nature, preserving most of its integrity from its head node, also known as a genesis block, because every block in the chain has to have a link to the previous node. But obviously, that's got to, not every node is going to have a previous node. Eventually, you're going to get to the head of the list, so that's the genesis block. It's a peer-to-peer distributed system, meaning it is entirely decentralized. There is no central server entity that is controlling all of the data and the workflow and how everything works. Everybody's working together in order to make the system run and work. So every single node has a copy of the entire blockchain, meaning that modifications require consensus amongst users. So one block cannot necessarily just modify everything. It's going to attempt to modify, and then every other block in the chain, or every other node that owns its own copy of the chain, is going to verify through like consensus whether this is something that it's going to allow to avoid malicious use of the peer-to-peer system. Timestamps are used and verified in many ways, but mostly use proof of work implemented from Bitcoin in order to preserve the integrity of the blocks. So essentially, uh, some sort of time intensive, not too time intensive, but computationally extensive task in order to avoid spam. Um, what's it called? Yeah, spam. So that for things such as DOS and DDoS attacks. And this is just a illustration showing somewhat what it looks like. You can see that there's three nodes or three blocks here, each containing a block header containing the parent block hash, which is the previous. It has its own hash, and it has that transaction counter, and that's the bottom portion of it is all the data within the block, which is going to depend upon the implementation of the blockchain, whether it's used for crypto or just maintaining documents, or just whatever somebody wants to use blockchains for.
So now we are gonna speak towards Byzantine fault tolerant, or tolerance in that case. So this in itself is sort of describing one of the main concerns with like security within blockchain. So more specifically, it's described with sort of a story or allegory of a Byzantine attack in which four generals are to attack a castle, but they are of course an equal distance away from each other and very far that the messengers, and the attack is only successful whether all four attack or all four perhaps retreat, never one disagreeing with another, so remaining meaning that they all are sort of synchronous in this attack. And this sort of consensus is sort of what is the baseline of what blockchain technology is, as we mentioned before, with sort of a 51% consensus and approval. So because of this, people usually highlight that certain blockchain technologies are Byzantine fault tolerant, meaning that they are in self decentralized enough to allow a general consensus to work for them in order to prevent sort of bad actors or malicious data or malicious blocks, as previously mentioned before. So now we go into core architecture of proof of work, sort of another sort of verification or another thing to prevent sort of malicious intent. Other ways to ensure the integrity of the blockchain utilize a concept known as proof of work. Originally designed as a hash cache to prevent malicious emails, it was designed in 1992 and implemented in 1997, and it's also used to prevent DDoS attacks. This proof of work concept basically uses some sort of computational data or some sort of computational amount of power from the PC in order for perhaps a new block to be added to the chain. So in this case, we're going to use Bitcoin because uh, one, this Bitcoin was probably one of the pioneers in implementing this, even though it's still relatively new, and two, it's quite honestly one of the most popularized examples. So, given a blockchain such as Bitcoin, proof of work ensures that a new entry added is valid. A miner can add a new entry to the blockchain by completing a computationally expensive task in order to receive a benefit or payment. An example, 0.0001 of Bitcoin. It's lottery like and ensures that a block within the middle of the chain cannot be modified. This in itself is usually done with sort of a challenge and then a hash that seemingly matches after that challenge, or a sort of like a finding the original string to a hash. And this computational data is simply made with the intent that if something were to be modified in the middle of the blockchain, perhaps, that the rest of the following nodes connected will also have to be modified and also would have to go through the consensus check of 51% of users verifying whether this was malicious or not. So now we're going to go on to its applications, and one of the many first is blockchain and technology in cloud storage. So typically, you could do storage verification using a blockchain. So data is sharded from the user, and it's used to create a hash Merkle tree. The hash is created between the cloud storage server, and then the copy of the Merkle tree are stored. Then the data is verified using a smart contract to compare the sharded data with the original data. So this is in order to verify perhaps maybe even some compression schemes, whether it was lossless or not. It's more or less to verify the integrity of the entire data. This is simply done with blockchain. Database functionality is also another one where BigChain DB is described as a service with high throughput, low latency, powerful query functionality, decentralized control, immutable data storage, and built-in asset support. BigChain DB is like a database with blockchain characteristics. It's Byzantine fault tolerant, meaning it has some sort of proof of work concept. So this in itself is open source. Many of you could go check it out, and is actually funded by its own ICO, meaning perhaps like its own coin in Series A. But this database functionality basically uses blockchain technology as its sole basis. And with that decentralized aspect and immutable data storage, most people can rely that they preserve anonymity as well as the integrity of their data rather than hosting it on one large server, as previously mentioned. So we even go into this as with mobile payments as well. Money itself is a construct that most of us abide by rather than like we actually have. So in a world that's getting increasingly electronical, given the current state of the situation of what's happening right now, you could see in this diagram to the right that the customer sort of goes to the bank in order to do the exchange of an exchange of goods, I guess, in terms of price. And typically we are charged to our account after. So rather, we receive the charge to our account saying, hey, this was purchased. We are charging the account directly. So it's sort of some sort of handshake between whose money it really is. But in this case, in this simple diagram, we're going to be saying it's the bank, and then the merchant also having their bank. So money starts to become more of a construct the more electronical it gets. So given that that's happening, security is a major concern for these large corporations. So these corporations have third party companies where they're hosting all their data, and it starts to get a little difficult as to whether this data center could go down, or some sort of synchronization error to where values are not correct. It was as recent as earlier this month. I have heard Chase Bank was having issues in displaying information for accounts. So a mobile payment system uh, could actually just use a decentralized blockchain technology. So a blockchain decentralizes a transaction itself and ensures security with a ledger, meaning that most of the transactions are recorded sequentially with the chain, and requiring the 51% consensus from users rather than the actual cloud storage providers. So instead of relying on AWS or Azure, etc., you would seemingly have your own sort of database and sort of nodes with your respective users. We also have this with Internet of Things smart home. So the modern smart home has only begun its major popularity with, I mean, as recent as Spotify giving free Google Homes. That's how I actually got mine, and Apple's new unveiling of the HomePod. So the smart home is quite honestly becoming the new industry right now. Everybody is not a lot, or I can't generalize everybody, but most people, I would assume, sort of iterations of this technology exist, are purchasing these technologies. So given how interconnected a smartphone is, or a smart home is, it's a lot of data that's seemingly shared. A smart home seemingly contains your name, your information, your location data to display weather, uh, your music interests, your schedules, your planners, your email, your notifications. This is all based off of Google Smart Home and what it could do and what it could hold. So, given that all this information is stored within perhaps the central server and your Google Home, uh, it starts to, or Google Home is an example, it starts to kind of get muddied up in that your information is compacted and seemingly vulnerable in the open world. But with blockchain technology, you can mitigate issues of security and system wide data integrity. So, uh, with the general consensus again to modify such important data because you have nodes, so malicious or bad actors couldn't affect it as much. The only issue with this that it's really difficult that these systems um, could have this technology because they're embedded systems with very low power consumption and very low CPU usage, so or very low CPU power. So that sort of creates that issue that could it really implement a blockchain or copy the whole thing and work with it? But as recently within this decade, we could see that light nodes are used rather than full nodes with Bitcoin and other cryptos, because you could use your phone for some of these technologies, and it's really interesting. Again, it is very young, but given as time progresses, we can start to see that CPUs, more or less in themselves, don't really have as much power draw as much as they used to. So a sort of power draw to performance ratio would perhaps vary, and we could possibly hope that we could have smart home devices that work on a blockchain for the sake of security. So now I'm going to pass it back to Arturo.
All right, so back to the topic of cryptocurrency, because after all that we just talked about, its other applications, this is the main, the starter. This is what started it all. Cryptocurrency such as Bitcoin and others were created in an effort to decentralize the exchange of currency and separate it by being controlled from a single entity. Without a central server entity, there would be no subjective or artificial inflation by one entity. So no human decision. It's all just controlled by a mathematical algorithm. Um, so yeah, and it's also more secure because of the consensus requirement, which we've mentioned already, which stops double spending of the same coin, which is a risk unique to digital currencies. Because in the real world, with like cash or other physical types of money, uh, you have to physically exchange it. But with this, if someone could maliciously create a false transaction, they could spend the coin, but not really spend the coin. They only gain from the transaction, but they don't lose. So they can essentially respend the same coin. But because again, this is all peer to peer, and everybody has to agree, in a sense, then uh, it's not impossible. The creator of Bitcoin, for example, has self-admitted that blockchain isn't impossible to hack. It's just really, really difficult and impractical. You would have to essentially own enough CPU power to overpower 51% of the network, which I don't know if anybody in the planet has that much computation power and is willing to just use it to completely overthrow Bitcoin. But essentially, it's almost impossible to hack. And although growing in popularity, one potential problem in the proof of work mechanism is the waste of computations. Like we mentioned, another part of why it's so secure is through the proof of work mechanism. A transaction will take, or not a transaction, a block being added to the chain will take, on average, it seems around like 10 minutes. And that's mostly because of the work that it's being put through to avoid spam or malicious attacks. But that work is by design just meant to waste time and computational resources to make it really impractical to, like I said, overthrow the peer-to-peer system. But it's not actually, at the moment, not being put towards any meaningful computations. It's mostly just wasted. Computation is just meant to waste time and resources to make it really to just discourage it. But currently, work is being put to possibly updating the proof of work mechanism in order to make it keep the positive of wasting not wasting resources, still using resources in order to prevent DDoS attacks, but having the computations actually contribute to the system or something else, to only have positives in a sense.
So that is our presentation. So now these are most of our sources, or all our sources actually. And if you guys have any questions, we will now go over to the Q&A. And yeah.
Thank you.